I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Okay, our speaker tonight is Dr. Stephen Bates. He's a postdoctoral researcher in 2 departments at UC Berkeley, both statistics and double ECS, electrical engineering and computer science. So I guess that's almost 3 departments. I'm told by experts in statistics who also happen to love basketball that Dr. Bates has the high honor of working with the Michael Jordan of statistics, whose name is, in fact, Dr. Michael Jordan. Forgive me. I think everybody introduces Stephen this way, but it's too good, and yet it's true. Before coming to Cal, to UC Berkeley, Stephen earned his PhD in statistics at Stanford, where he received the Rick Weiland Graduate Fellowship and was honored with the Theodore Anderson Theory of Statistics Dissertation Award for his PhD work. And even before that, Stephen was highly accomplished, earning statistics and math degrees at Harvard, and spending a year teaching mathematics at the little-known, to me anyway, the little-known adjunct of NYU in Shanghai. He taught at NYU Shanghai. I must also brag a bit about Stephen's important involvement in the Wonderfest Science Envoys. He was indeed a Wonderfest Science Envoy. These are PhD students who want to be even better science communicators than they already are. Wonderfest provides monthly workshops for about a year where these PhD students become more skilled at the art and science of science communication. Tonight, Dr. Bates is exploring with us uncertainty in artificial intelligence. Can AI know what it doesn't know? Please join me in welcoming perhaps not the Michael Jordan, but certainly the Stephen Bates of statistics, Wonderfest Science Envoy, Dr. Stephen Bates.
All right, thanks a lot, Tucker. That was great. So I'm excited to be here with you all, especially because this is in some ways my final exam as a Wonderfest envoy. So I really appreciate all of Tucker's mentorship over the years. So we're going to talk a little bit today about artificial intelligence. It's on a lot of people's minds these days. And we're going to take a kind of, I'll say, sober-minded view about what it can and cannot do, and we're going to kind of really dig into it in a level of detail that you may not have seen before. And in particular, we're going to talk about things where you're not sure or if you can do it, or you want to kind of be aware of the uncertainty in a difficult task that you're doing. And when we talk about that, we're going to need to talk about statistics, kind of an old-fashioned subject that is extremely relevant here. All right, so AI. If you just open up the New York Times or go to the bookstore, you're going to see many, many articles about artificial intelligence. So one from a few days ago in the center, can machine learning learn morality? So machine learning, AI are kind of synonyms for the purpose of today. On the left, we have The Economist, Artificial Intelligence, the Promise and the Peril. An article from just earlier this month. So Zillow, a home buying company or a real estate company, had an algorithm, an AI algorithm that was automatically buying homes, and then all of a sudden they kind of started to do the wrong thing, and they had to shut it down really fast, and they accidentally purchased far too many homes. So that's the article you have in the bottom. And on the right, even the New Yorker is getting a piece of the action. The traditionally, literary magazine, but AI is kind of on everyone's minds. Okay, and I'm sure you've seen many of these things yourself. So. What is AI? We're going to talk about that a little bit, and we're going to talk about what we can do with it and what we can be really, really confident that it's going to work or not work, basically. Okay. Something that's really near and dear to my heart is using AI for scientific discovery. So it's not just about building products for say Facebook or something like that. You can also do things like automate scientific processes. On the right-hand side, we have this Wired article as it is. Robot makes scientific discoveries all by itself. Okay, so in this case, it is a kind of like all-in-one chemical laboratory. The system has ways of kind of mixing different components, testing them out for various desirable properties, and then looking to see if it worked, and then having an idea for the next set of chemicals to try. So you have this robot that can just by itself, for days and days and days, kind of do chemistry experiments. In general, science is going through this kind of data-driven revolution where we now have these really immense sensor arrays to kind of gather data about basically all scientific phenomena. And then we have all this data and we need to search through it somehow. And increasingly that's being done with these AI algorithms. Okay, so a lot of science even is now the purview of AI. And one thing I want to stress for the purpose of today's talk is that AI or machine learning is kind of a different way of learning about the world and a different way of doing science than what we've done in the past. Okay, so these AI methods are what I'm going to call black boxes. We create these computer programs that are very complex. We don't know exactly how they work, but we know that they do work in some sense. So the black box here is this big collection of pipes. I can't tell you what it's doing or it's not doing, but I can look at some of its properties. So I can say this is kind of accurately mimicking something that I can observe in experiments, or it's accurately mimicking, say, the decisions a human would be making, but I don't know how it's doing that. Okay? So let's contrast this with kind of classical science, or the way people would reason about the world before. So we have some of the scientific greats: Isaac Newton, Charles Darwin, Mendeleev, physics, chemistry, and biology. And if you think about their contributions, they were all kind of concepts or laws that were meant for humans to understand in some way. So on the left I have Isaac Newton's laws of physics. It's Newton's 3 laws. They're these equations that tell me, they predict what's going to happen with a physical system in just about any situation. Okay, in the center, kind of somewhat qualitative, somewhat quantitative, we have the periodic table. The periodic table is a way of organizing information that allows me to make predictions about what's going to happen when I kind of mix new chemicals, or I can postulate maybe that there are chemicals that I have not discovered, and so on, elements that I have not discovered, and so on. And on the right, Charles Darwin, of course, the theory of evolution is a concept that helps us explain patterns that we see in nature. So all three of them are giving us kind of a lens to view the world that is meant for me, a person, to think about what I see and to catalog and organize information that I see. Okay. And going back, AI is not really this. It's a large computer program that can extract certain bits for me, but it's not a kind of cleanly stated theory. It's not Newton's 3 laws that I get to use. It's something else. It's kind of like a really good simulator that I can ask certain questions from. Okay. So we're going to think about the consequences of this for science, and we're going to kind of use this to dive a little deeper and think, what exactly is going on in this black box to the extent that we can unpack it, and what are the consequences of only having access to a black box. All right. So with that, I will jump into the first part of the talk. So an insider's view of AI. We're going to look at some machine learning or artificial intelligence systems in a lot of detail. So you can think, as you think about Zillow and you think about their algorithm failing to price homes correctly, we can think about how did that happen, or how would something like that happen, and how can I make a better version of it, and how can I validate it, and so on. Okay. So we're going to look at AI in probably more detail than you may have seen in the past. All right, in order to do that, I'm going to tell you the story of probably the most important thing that's happened in AI in the last 10 years, which is called Imagenet. Okay. Imagenet is a database of images together with labels. The images are kind of the things you see on the bottom. So on the left, I have a sewing machine. The center, I have a tiger shark. On the right, I have a Christmas stocking. And there's a collection of about 1 million such images paired with labels. Okay. So this by itself seems kind of humble, but it actually is, again, the most important thing that's happened in machine learning in the last 10 years. So these images, so why is it so important? It's because in order to successfully create these AIs, what they really need access to is lots and lots and lots of data. And this was the first kind of concerted effort to create a high-quality data set at this internet scale that we see today. Okay. So Imagenet is about 1 million images, And the images are each in one of 1,000 categories. So the categories, again, are things like sewing machine, tiger shark, Christmas stocking, and 997 other categories. How this was collected, which was kind of the secret sauce, is this researcher now at Stanford named Fei Li created a system that scraped all of these from the internet. This was in about 2007 to 2009. And then they dispatched all these images to a lot of different people to label them. Okay, so image of a sewing machine would come up on my screen and it would ask me, what is this? And my option was things like sewing machine or tiger shark, or I could say nothing, that's not an image that belongs in this database. So they did this 1 million times, they gathered this great data set, and this then became the favored test bed for machine learning. So again, the secret sauce here was collecting images, but at internet scale. In order to do that, they needed to create this kind of automatic, or this crowdsourced labeling system. So that's what I'm showing in the top right. They gathered all these images from the internet, they dispatched them to people on Mechanical Turk, and then they made sure they were consistent across several people and so on, until they had 1 million images. Okay. Again, this is, it seems like kind of a natural thing now. In 2007 to 2009, it was not such an obvious thing to do to crowdsource a kind of high-quality scientific data set.
Stephen?
Yeah.
Do you mind questions during
Oh
the
yeah,
presentation?
please jump in. Are there any questions?
I've got a quick one.
Okay.
I've never heard the word Turk used in this way. What is it?
So Mechanical Turk is a specific Amazon platform. And the way it works is you or anyone else can go on and you can create a set of tasks that get dispatched. And then people can do those tasks for money. So you can go on and it'll show you an image. And then if you click sewing machine, you get 5 cents. And you can do this over and over and over, and you can say make money labeling images. So you can do other things besides machine learning labeling, but it's this kind of system where you can put jobs on it, and then people on the other end can do those jobs and make money for that transaction.
It's my retirement plan.
Yes, if it comes to it. I think you would be an excellent machine learning image labeler. The word Mechanical Turk here is just a bit of historical trivia. It comes from this kind of mythical chess-playing machine where it was supposed to be kind of like a machine playing chess, but the trick was that they're from the 15th century or something like that, and it was called the Mechanical Turk. But the trick was that underneath the machine was a person actually making the moves. Perhaps somewhat metaphorical for machine learning in some ways. Okay, so again, the secret sauce here.
We have a little more questions.
Oh, I apologize. Thank you.
So these 3 items that you're choosing, why did you choose them? And are they kind of, when you're talking about the millions, are they like you're slicing and dicing all the different pieces, parts of that,
These 3 images?
Yeah.
Yeah, so there's, like, the sewing machine is 1 image. There's about 1 million images, and, about 1 out of 1,000 of those are sewing machines. So there's about 1,000 different pictures of sewing machines in this database. And each picture of a sewing machine has a kind of another piece of data attached to it that says this is a sewing machine. So there's a bunch of images, and they've also been labeled by a person. Okay. So there will be 999 other sewing machines, and 999 other tiger sharks and Christmas stockings and so on. So there's also dogs, cars, fighter jets, things like this. Okay, all right. So we've gathered this really big data set. Us being the research community in 2007 to 2009, and what do we do with it? Well, the way machine learning research and AI research progresses, this is the real workhorse. It's called the train test paradigm. So what happens is you set up a game, you set up a competition using this data set, and you take, we'll say 80% of this data set, so 80% of these 1 million images, and you call that the training set, okay? And you send these out to everybody, and you say, here are these images, you can do whatever you like with them. And the rules of the game are, there's no rule for you, except that I'm going to grade you on some fresh images. So I had 1 million images. I sent you 80% of those at random, and I kept 20% myself secret. Okay? Now, you can do whatever you want with your 80%, but what you're going to do is I'm going to grade you based on how well you do on my 20%, the ones you've never seen before. Okay. Now, this sort of setup is really useful because it allows people to kind of use any sort of creativity they want to get good answers. And there's only one rule. The rule is do as well as you can on the fresh data. Do as well as you can on my 20% of the data. So this is how it goes. This is, people will then take this 80% of the images, so 800,000 images, and they'll try really hard. They'll run these algorithms, deep neural networks and other models on this 80%, and then they'll kind of constantly evaluate themselves, and at the end of the year, they get to submit their final answer, and they see how well they do. All right, so they did this from 2010 to 2017. And what I'm plotting here is the accuracy on that unseen data. So I had my 20% data that I didn't show you. You did the best job you could with 80%. And then I graded you on the unseen data. And in 2010, the best anyone could do was about a 28% misclassification rate. So they got, 72% of the images correct. So they were able to say the sewing machine is a sewing machine, the dog is a dog, and so on. They were able to get that right all except for 28% of the time. Then step forward in time 1 year to 2011. That number went down to 26%. Lower is better. Lower means less error. Fast forward to 2012, it drops down to 16%, and so on and so on and so on. Okay. Now, 2012 is a bit of a watershed year. It's a bit of a kind of big deal in my field. Does anybody know what happened in 2012? 2012 was the year that people started using deep learning. So if you've heard the term deep learning or neural networks, 2012 there was this new entrant to the contest called AlexNet, named after a person, Alex. And AlexNet was, as you can see, there's a pretty big drop off from 2011 to 2012. That was when people started using deep learning. And then every year thereafter, the error kept going down and down and down. And in 2017, the error rate was about 2%. So, previously, remember, it was 28%. Now it's 2%, 8 years later. And they decided that this was too easy, and they moved on to harder problems. So 2017 was the last year. They played this game with Imagenet. They still play similar games, but not with this exact data set. Okay. All right, so you can see the progress is pretty dramatic here. And again, it's really enabled by setting it up as this game where you're allowed to do anything you want. You can be extremely creative, drive the metric down. It's just, I'm going to grade you on fresh data. And this is how all AI research works up to the present day, for the last 10 to 15 years. Yeah, Tucker.
The human error rate is rather steady there at 5%, meaning an average person can get 5%, 5 out of every 100 correct.
That's right.
They know that's a sewing machine. They know that's a tiger shark.
Yep.
And they know that that is your Christmas stocking. But for me, tiger shark, I had no idea that was a tiger shark. So you can't be an expert, right?
Yeah.
We're assuming a certain really average human. That's easy to define?
Yeah, so how would you, so the 5% there is just for reference, take it with a grain of salt, but how would you get such a number? You would look for agreement among people, right? So I would give the same image to like 1,000 people, and then I would kind of check how often people agreed with each other on that image. And bear in mind that the tiger shark, you might not know immediately it's a tiger shark, but there's only two kinds of sharks in the data set. So there's tiger sharks and there's great white sharks. And so as you explore the kind of tree of possibilities, you might not immediately know it's a tiger shark, but you would probably, if I asked you is this a tiger shark or a great white shark, you might be able to get an answer. And 5% is really just kind of for reference. Is there another question? Okay. All right, so this is Imagenet, and again, in 2017, they kind of moved on to more complicated prediction tasks, but still prediction tasks. All right, so in 2017, again, they called off Imagenet. Has Imagenet been solved? Okay, so let's, again, we're kind of putting on our critical thinking hats about AI right now. In some sense, we have solved Imagenet, and in what sense is that? Okay, I have this piece of code, this black box, that is now amazingly accurate at taking images I have this piece of computer code. I take an image of a sewing machine, and it almost always says sewing machine. I take a picture of a tiger shark, and it almost always says tiger shark, and so on, and it only gets it wrong 2% of the time. All right, so that's pretty fantastic. This is an amazing accomplishment. But I just want to point out that what we're really doing is we have a piece of code that can mimic what a human would say, and we can do a little better. It can mimic what a group of 1,000 people would say. But how does it work, and in what sense does it know that this is a tiger shark? It's a little bit harder to put your finger on, but one thing nobody can argue with is that it's doing a great job of labeling the images. Okay. But again, unlike Isaac Newton and Charles Darwin and so on, it's not clear that it has a kind of really crisp scientific description of a tiger shark. It's more that it just now knows how to, it knows which images a person would say are a tiger shark and not. Okay, so again, just to recap what we know, this black box, this piece of code that we have created and kind of know how to systematically create, we know that it works 98% of the time on this exact data set. Okay. Some things that we don't know but might be true, might not be true. Will it work next year when the images come from different cameras? Maybe, maybe not. In this case, probably, but we have to kind of think about that. Okay. Can it help a self-driving car detect people and animals? Maybe, maybe not. Again, what I know is it does a really good job on this data set of images, but what does it do in the wild? It's a little harder to say. Which images are hard? For what images will I input here? Will it kind of say, not do a good job? Will it fail? Not immediately clear. Now, all these questions are things we could ask and we could answer, but they don't jump right out from that 98% number. They're sort of different properties that we have to think about. So, in summary, yeah, please.
Okay, the pictures you got of the tiger shark.
Yep.
So this system can detect that that's a tiger shark.
That's right.
Okay, is that the same picture of the tiger shark throughout, or are they different?
Oh, they're completely different pictures. Yeah, they're just totally different pictures. However, they are all they're all taken from the internet, and so they are all typically the shark would say be in the middle of the picture and so on. So there are some systematic features of these images due to the way that the data is collected, but they are different. They are different pictures. Yeah, thanks. Okay, so this machine, yeah, they're deterministic. So when you put the same thing in, you always get the same thing out. So this thing is very useful, but it's limited, and we have to understand its limits. And that's where we're going to need to think about, okay, so we're going to think about understanding a very complex system. It turns out there is a scientific or mathematical discipline for doing that, and that is probability and statistics. Okay, so that's what we're going to talk about now. But again, the relationship here is I have this black box piece of code, I have this piece of software. It works really well in some sense, but I don't fully understand how it works, so I'm going to need to kind of think about how I can evaluate it in a rigorous or precise way. Okay, so when we think about uncertainty, again, there's a scientific or mathematical discipline devoted to understanding uncertainty. So here's a quote from Laplace, a mathematician from the 18th century. It's about, in general, why we would care to study something like probability. So ignorance of the different causes involved in the production of events, as well as their complexity, taken together with the imperfection of analysis, prevents our reaching the same certainty about the vast majority of phenomena. So in contrast to physics is what he means here. Thus, things are uncertain, things are more or less probable, and we seek to compensate for the impossibility of knowing by determining their degrees of likelihood. So we need the science of chance or probability. So what he's saying here is when we look at things that are not quite as perfect as Newton's laws, when we look at things that are complex, we can't know every single piece about how they're going to work, but we can think in broad strokes about what they're doing using probability and statistics. All right, so that brings us to the next part of the talk. So we're going to talk about statistics, or making AI reliable, I'll say. What can we do to take these really great pieces of software, these really great pieces of code, and be 100% sure that they're working and doing the things we want them to do. All right, the first thing we're going to talk about here is confidence intervals, which are, again, one of the greatest hits from statistics, one of the most classical topics. Okay. So confidence intervals are a way of measuring uncertainty. So they're a way of making it precise. What do I mean when I say I'm uncertain? And in particular, the way they work is they ask the following question. There's something I don't know about the world. What values of that thing, if it's a numerical parameter, are kind of consistent with what I've seen so far? Okay, so I can't know everything about the world, but I can narrow down the space of possibilities of what's true or not, and then I can report that as kind of my range of plausible values. This is a concept that goes back to Jerzy Neyman, a statistician who spent actually quite a bit of his career here at UC Berkeley, so just across the bay. He originally from Europe, he then moved to Berkeley. Okay, so how do confidence intervals work? You may have seen them before, but I'll refresh your memory in any case. So suppose we're trying to think about a number that in this case is the probability of flipping heads. So I have an unfair coin. It could be heads, it could be tails. And there's some probability being heads, but I don't know what it is. I get to observe the coin 100 times, but I don't know the ground truth. I don't know exactly how likely it is to be heads. Okay, let's say I flipped it 100 times and I saw 32 heads. And then I asked you, what is the probability that the coin is heads? Or what is kind of that ground truth number for how likely it is to be heads? What would your guess be? Okay. All right, so you should probably first guess, it's going to be something around 32%, right? But I also know it's probably not exactly 32%. Maybe it's 31%. Maybe it's 33%. Is it 80%? It's probably not 80%. Is it 10%? It's probably not 10%, and so on. So you can kind of do this thought experiment in your mind. Jerzy Neyman taught us how to do it kind of fully precisely in a lot of different cases. Okay. In this case, if you do the calculation, so you actually do the math out, and you ask exactly that question that I asked you, could it be 31%, could it be 30%, could it be 29%, and so on, and you go through the list, what you'll end up with is this interval from 22.9% to 41.1%. So that would be a 95% confidence interval for what the probability of flipping a heads is, given that you've seen 32 heads out of 100. Okay. And again, the logic here is I compile all of the states of the world that are consistent with the data I saw. So I saw 32 heads. I would say that 23% is consistent with that, whereas 10% is sort of inconsistent with that. Okay. All right, so this concept has existed for a long time. How is this going to relate to the sorts of things I do with these AIs, with these artificial intelligence algorithms? Well, the first thing we might ask is when we're making predictions, instead of just kind of making guesses about things, I might ask for something like a confidence interval. So what would a confidence interval look like? So here are 3 images, and they're all from Imagenet, that data set I told you about before. And they're all images where they are actually a fox squirrel, but they're images of different difficulty. Okay? So on the left, I have a very simple picture of a fox squirrel. The reason it's a simple picture of a fox squirrel is because the squirrel's right in the middle. You see the whole thing, and it's in a background that's kind of common for a squirrel and so on. So an algorithm can pick that out quite easily. In the middle and in the right, I have images that are more difficult. The middle image, which is also a squirrel, is more difficult because the squirrel's at a strange angle. And the right image is more difficult because the squirrel is partially cut off. Okay. And in fact, I'm not actually sure if the image on the right is a squirrel or a marmot, but it's labeled as a squirrel in the data. Okay. Now, what I might ask is, my algorithm, remember that big black box piece of software, is going to spit out a guess. So I'm going to hand it this image and I ask it, what is it? And in this case, it says fox squirrel. I'm going to hand it this image and I'm going to ask, what is it? And I might ask that when I give it a hard image, it gives me a confidence interval, or in this case, a confidence set. It's not an interval because the options are kind of a distinct set of things. It could be gray fox bucket or something else. And I'm going to ask it to give me a set of values. And I'm going to ask the algorithm to give me something that's right 95% of the time. Okay. So this is now like a confidence interval, except for the output of the model, for the output of this AI algorithm. Okay? So there's specific ways of doing that, and I fit an AI to do that in this case. And in that case, what it does for this image, which again is a more challenging image, is it outputs now fox squirrel, gray fox, bucket, or rain barrel. So when I give it a more challenging image, it doesn't know exactly which of those is correct, but it says fox squirrel, gray fox, bucket, and rain barrel are all reasonably consistent with the image you gave me, and I cannot tell you which one it is. Similar story on the right. When you give it this image, it says marmot, fox squirrel, mink, weasel, beaver, and polecat are all consistent with the image you gave me, and I'm not sure which of those it is. So this is my confidence interval, which is now a confidence set, on top of the artificial intelligence algorithm. So you can see that now we have a sort of richer output than if we just asked the algorithm to hand me its best guess. Now the algorithm is telling me both its best guess, and it's telling me kind of how certain it is. If the set is really big, it means I'm not sure what's going on. If the set is smaller, it means I can tell you exactly what's going on. Okay. For example, on the left. Okay, so where did these confidence intervals come from? So topics like this are something I spend a lot of my time thinking about, a lot of my time researching at Cal. I'm going to walk you through this example in a little bit of detail. We'll do just a hint of math, just a hint, to see where things like this come from, and you'll actually get to see techniques that are really used for problems like this in machine learning systems. Okay, so where did these confidence intervals come from? So we're going to do that thought experiment that I told you. We're going to hand this image to the algorithm, and then we're going to ask the algorithm to self-report how consistent is the label fox squirrel with this image. Okay. All right, so we're going to do that, and how do we do that? Well, what's going to happen is there's going to be this function, s of xy, and it's going to be a number, and that number tells me how much the model thinks the image x fits with the label y. Okay, so in this world, x is always the image. That's just the notation that's always used. Y is always the label. The label means squirrel or sewing machine or something like that. Okay. So there's just, inside the code, there's a little subroutine or there's a program that spits out this number, and the number is how much do I think squirrel fits with this image, or how much the model thinks squirrel fits with this image. But can this number be trusted? And this is the thing. Remember, the model is just this really big collection of pipes running all over the place. I'm not really sure it's working or not. If I want to convince myself it's working, I need to look at the data. So what I need to do is I need to take this number, this S, the score that tells me how good the image is with the label, and I need to validate that. I need to make sure it's actually doing what it's like. It's actually working correctly. So how would I do that? Well, what I do is I take the scores with ground truth. Okay, so I go back into my Imagenet data set. I look at some cases where I actually know it's a tiger shark. I take an image, I take a tiger shark, and then I compute this number, s of xy. Okay, so the important thing here is I did this with the real y, the true y. And I'm just going to plot those numbers. Maybe this number is 10, maybe this number is 0.5, and so on. And I'm just going to plot them from less consistent to more consistent. So again, this is ground truth. This is solid information that I'm promising you is correct. Yeah, Turk.
Stephen, the S is a number.
S is a number.
Indicating the match between the picture and the label.
That's right.
So perfect match is S equals 1?
We'll say that a perfect match is, we'll say a perfect match is 1. So bigger is better. Bigger means more consistent, and we'll say that 1 means perfect consistency. It's never going to say exactly 1, but that's okay.
Okay, would you expect, I'm not understanding the array of blue dots. Why is there so much spread?
Oh, yeah. Don't worry about the scale. The point is the algorithm's spitting out numbers. They can be, we don't exactly know how it's going to work. But what we have to do is we have to look at those empirically. So maybe in a perfect world, there's a big pile of blue dots here, but we have an imperfect world, and we're trying to figure out how imperfect or perfect this world is. So far, this is just kind of observed data about the world, and it sort of is what it is. And then we're going to benchmark relative to this. So whether it's working or not, we're going to judge kind of based on things that we've seen are true. So all these blue points are true points in some sense. Okay, so now I get a new data point like this squirrel, and I'm going to do this thought experiment again. How consistent is fox squirrel with this image? But now I don't know that this image is a squirrel. I'm just going to try out every possible label. So first I try out fox squirrel, and it falls over here, which is in the more consistent range. And in particular, it falls to the right of a lot of these blue guys, which is good. If it falls to the right of a lot of blue guys, or on the more consistent side of a lot of blue guys, that means it's more reliable, or the model has judged it to be doing a good job. I'm going to play the same game with another label, fox squirrel, and maybe when I plug in fox squirrel, it ends up right here. So again, I don't know that, for the blue points, I know the true label. Right now I'm playing this game when I don't know the true label. So you gave me a fresh point. I didn't know it was a squirrel. I was trying to figure out what to do with it. I tried squirrel. I tried gray fox, and they both looked okay. So it could be a squirrel, it could be a gray fox. And then I tried refrigerator, and the model said it's definitely not a refrigerator. Okay. So what I do is I collect all this information. I try all of the options. I try fox squirrel, gray fox, refrigerator, and so on. And I see if they're more or less consistent. And then I collect the ones that are consistent into my final answer. So fox squirrel here was, it turns out the scale was 0.82. Gray fox, bucket, and rain barrel were the three that passed the test. Okay. And now to Tucker's point, what does it mean to pass the test, or what do these blue points mean? What I do is I make a cutoff here at say 95% of the blue points, and I take everybody that's to the right of 95% of the blue points. So I don't know what the right cutoff is a priori. This algorithm is doing something quite complicated. But what I do is I let the data tell me that. I look at examples where there's ground truth, and then I cut it off based on that. So I cut it off based on, say, this 95% mark. Now, there's actually, if you think about this for a little while, you can convince yourself that this is actually going to work 95% of the time. Unless I get really unlucky, and it turns out that the ground truth was way over here. Like, it turns out when I plug in fox squirrel, I ended up way over here, which is kind of a rare thing to see. The correct label will be in this confidence set. So I won't go into the details, but the main point here is the yellow point with the correct label has the same distribution as the blue points. The blue points were examples of points where I gave you the right label and the image. And so when I give you the right label and I give you the image, when I give you the right label, but for this kind of one where you didn't know or not, it will follow that same distribution. Okay. So we're kind of using that to benchmark new points. If that calculation isn't sort of clear to you, that's okay. The main point is we kind of empirically tested these confidence intervals and made sure they were 95% confidence intervals. So whatever that big pile of pipes that's telling me that this squirrel is a squirrel is, however that thing is working, I can promise you that I'm getting it right 95% of the time. Okay, so we did that, and now Jersey Naaman, our old friend Jersey Naaman, he's very happy. You can see his big grin on his face. We have now created AIs that give us confidence intervals, and we're kind of back in the land of statistics. Okay, now these confidence intervals are quite important, so I'll give you some examples of AI problems where you would want such confidence intervals. AlphaFold is a kind of recent breakthrough in artificial intelligence, and in this case, molecular biology. It's related to a protein structure prediction problem. So what happens is I give you a sequence of amino acids. Amino acids determine the structure of the protein. I ask you, given this sequence of amino acids, what is the three-dimensional structure that that protein is going to take? This is a very hard question because the physics involved is very complicated. So in principle, you could answer this just based on physics. However, in practice, you cannot because it's just the interactions among the different sites are just too complex. But what you can do, it turns out, is you can predict it quite well using these algorithms, using these models. And so last year in 2020, there's a contest set up, just like Imagenet, where I give you some amino acids and I ask you to predict the protein structure, and then I'm going to grade you based on proteins that you haven't seen yet. So they go in the lab and they measure the three-dimensional structure, and they do that about 20 times. They don't tell you the results, and they ask you to guess, and then you're graded on how well you can do on those extra points, just like Imagenet, but now for proteins. In 2000, let's see, this is 2018, AlphaFold, which is from DeepMind, the company in the UK, now owned by Google, became the leader. They scored 60% on this scale. It's some scale measuring how good you are predicting the 3D structure of a protein. And then in 2020, they kind of really blew everyone out of the water and got 85% on this metric. So now, far and away, the best way to go from a sequence of amino acids to a prediction about the 3D structure is through these algorithms, is through these black box algorithms. But when you do that, you definitely are not going to be satisfied with just one guess. You're going to want to know how well or how badly am I doing on any example. Is this a hard example? Is it an easy example? And so on. We want those confidence intervals that we had on the previous slide. Okay, so again, we're in this regime where I now have this piece of software that can kind of mimic or predict nature in a pretty good but not quite perfect way. But it doesn't fully understand it in the way we think about understanding physics. It's just kind of finding good rules of thumb to predict it. Okay, so I'm going to want, because I'm dealing with this kind of fuzzy or imperfect or kind of indirect knowledge, I want to be more rigorous about it. So we do things like put confidence intervals. So here's an example. This is a project I worked on last year. On the left, we have an amino acid sequence. That's the picture, an amino acid sequence that's been folded into a protein. That's on the left. In the computer, that's represented as this matrix of pairwise distances. So any entry here is talking about how far two parts of this protein are from each other. So it's just a way of your computer to store a 3D shape is to memorize how far apart any two parts of the object are. What you can do is you can put confidence intervals on that, and that's what we show you on the right. That's sort of the sort of thing I work on over at Berkeley. Questions? Okay. A similar task here, where you want confidence intervals on what the AI is doing, is something called object detection. So in object detection, you're given an image, or in this case, a video, and your goal is to do three things. You want to locate distinct objects. You want to put a box around them, or select a set of pixels in blue, like in a giraffe. And then you want to label it. And you want to do all these things with a certain accuracy rate. And so what you can do is you can build algorithms like the ones you see here. And what they do is they kind of create these bounding boxes, and they can give you confidence intervals about all of it. So you can't see it that clearly in this example, but around each, say, person or train or giraffe, there's a little confidence interval. And then the boxes in black, there's those white pieces of text. Those are the guesses from the algorithm about what the, so if I look here, there's a confidence interval around the size of the car. There's also a confidence interval about whether or not it's a car. You can't read that, but these labels here are something like person, handbag, scooter, or something like that. So every box has a guess about how big it is and what object it is. And all of these guesses, when I say guesses, are precisely calibrated confidence intervals. Okay. Another problem of this nature where I really care about getting it right. I really care about telling you exactly when I know what's going on or not. This is a tumor segmentation example. So we have these medical images that doctors collect. These are colonoscopy images. And some subset of these images correspond to tumors. And you want to build an algorithm that can automatically pick those out. So you want the algorithm to automatically say, for example, that this region is tumorous. Okay. So there's really good algorithms for doing that. And again, as you can guess from what we've been talking about up to now, the thing that we really want here is we really want to be certain, and we can express that uncertainty precisely using confidence intervals. And so what we have here is we have an algorithm that outlines the tumors, and I can promise you that it's getting 90% of the mass of the tumor correct. So you have these kind of conservative regions that are getting things 90% right. For just a tiny bit of detail about this one, how does the algorithm work? Well, inside the algorithm, there's this knob that kind of goes from more to less confidence. And you kind of look at it and you kind of spin it, and you see where it's giving you where you see where it's tuned correctly. So that parameter here goes from kind of like small sets to big sets, so it's how conservative or how aggressive I am at labeling a pixel to be a tumor. Okay. I'm showing you 3 values of that parameter in these 3 rows. So in the top row, I'm being quite, I'll say aggressive in that I'm selecting only the pixels where I'm very confident it's a tumor. And what you'll see is it's incorrect a lot of the time, or it misses a lot of the tumors. So red here is a false negative, which means it's a true part of the tumor, but the algorithm missed it. The algorithm said, that's not a tumor. Now, in the middle, you try kind of a better tuning of it, and you can see this one's about right. All the white you see means it's correctly detecting that tumor, and all the blue means it's being too careful. It's saying a non-tumor part is a tumor. Okay, so blue means you're being too careful. You made the predicted tumor too big. So in the middle, you see it's about right. There, you got all of the tumor, and you didn't take too much extra. And then on the bottom, if you tune this knob to the wrong place, you'll see that it's taking all blue, or there's a lot of blue here. And a lot of blue means it's being, it's like selecting almost the entire image. So I hand you this image, and the algorithm says the whole thing is a tumor. Okay. That's incorrect. It's, it's not, the whole thing is not a tumor. It's just that setting of the algorithm is the wrong one. What you really want to be is you really want to be in the Goldilocks zone, right in the middle. All right. Are there any questions about these last few examples before I move on to the next part?
Has this work been commercialized?
It hasn't been commercialized yet. No, it's in a paper that we put out earlier this year.
Are there any entities around the world that have commercialized it?
Not in exactly this form, but I think the answer is no. But there certainly are commercialized AI algorithms for some medical imaging tasks. I don't know about this particular task, but for the segmentation with confidence intervals, no. Okay, but there are cases more like the ones we saw previously where I would show you when I'd say, is there a tumor or not? There are things like that that are in production. Thanks. Okay, so with our last few minutes here, I'll talk about a slightly different topic, but still related to this general theme of I have this algorithm and it's doing some really cool things. How can I be sure that I can deploy it safely? We're going to talk about asking for help when you need it, or the statistical term for this is outlier detection. So we have some sort of, we have these algorithms, we're going to deploy them, and when something weird happens, we want them to tell us. Okay, so knowing when you want to ask for help. So here I have, this is some real chest x-ray data, and it's taken from the last year. The goal was to identify all of these x-rays as coming from healthy patients or patients with COVID-19. So in this particular case, the image came from a healthy patient, and the algorithm can detect that. In this case, it came from a patient with COVID-19, and the algorithm can detect that. And in this case, okay, what happened? Okay, so let's look at this image. Does anybody see anything weird with the image on the right?
Upside down?
It's upside down, right? Okay, yeah, that's right. So it's a chest x-ray image, it's upside down. For a person, this would be very simple to fix, right? The doctor would spin it around, and they would keep going on their way, and nothing would have happened. But for an algorithm, it's actually not so simple, right? There are cases where there are images like this in the data set, and the algorithm needs to say, wait a second, this is not what I expected. Or, I mean, in a perfect world, the algorithm could spin it around, but suppose it couldn't do that, at least we would want it to alert us that something had happened.
Would the algorithm do it by itself?
Ideally, yes, but it's hard to predict exactly which weird things could happen. So I could tell the algorithm, hey, if it ever looks like it's upside down, spin it around. But that's like one of a very small number of things that could go wrong. Yeah. In this case, though, we could build it so that it would spin. Yeah. Okay, so what do we do in some cases like this? Well, we want to build in some safety layers, right? We want to have some sanity checks that the things we're seeing are what we expect. And this has a name, again, it's called Outlier Detection. And this goes way, way back in statistics. So this is an academic paper from the 1969 called Procedures for Detecting Outlying Observations in Samples. Now you can bet that in 1969 they were not talking about AI algorithms or AI algorithms for detecting COVID-19, but nonetheless the math underlying it is all the same. I'll give you just a brief hint about what's going on here. So again, I'm going to walk you through just a teeniest bit of math just to show you how these things are calibrated, but it won't be too bad. It'll be even less than last time. Okay. So we're going to run through this thought experiment, which is, how strange is this image? Okay. In particular, we're going to have the algorithm walk through this thought experiment. So we're going to compute a number, s of x. There's no y this time. There's just an x because there's no labels. Okay. So x is an image. X is just a representation of this image in my computer. And I just have the computer do things like can kind of compare this to previous images it's seen and ask, how weird is this? Okay. Now, again, this number is also just coming from the algorithm. The algorithm is some complicated thing. I don't know what it's doing. So can this number be trusted? And our answer is, just like it was before, we're going to look at the data. So we're going to look at cases where we do know what's going on to kind of evaluate how reliable this number is or what this cutoff should be. The setup is, again, exactly the same as last time. I kind of look at some cases where I know the ground truth, and then I'm going to check my new point. Okay? So in this case, my number s is measuring how things go from less weird to more weird. If it goes too far off to the right-hand side, I'm going to say, I need to go find a person. I need to go find a doctor to look at this. Okay? So in this case, with this image, you're way off to the right, and you say, hold up, this is not something I've seen before. Not a normal input, right? Go talk to a doctor. If I hand you a different image, so the same picture, different image now, but the rest is the same. This image is right side up. What happens is I see I'm in the middle of the blue. And when I'm in the middle of the blue, that's a good sign. That means this looks like all the other kind of real trustworthy things I've seen before. So I'm not going to flag it. I'm not going to call the doctor. All right, so this one looks like a normal input. Excuse me. Looks like a normal input, which is great news. Okay, so these sorts of hypothetical thought experiments are really kind of the hallmark of statistics. What you do is you don't know what's going on in the world, but you try out a bunch of possibilities and you ask which ones are consistent or not. You ask which ones are consistent or not based on certain mathematical facts that you can derive about the situation. Now, again, just to recap, the things we've talked about today, we talked about how we have these AIs. Okay? The way the AIs work are we kind of set up a game where there's some rules to the game and you can do anything you want to maximize that score. And you want to do as well as you can on, say, predicting on my data or predicting on some fresh data. We have algorithms that are really, really good at this, but they do have some weaknesses. And in particular, since we don't know exactly how the algorithms are working, we need to be a little bit careful about how we deploy them. Being careful about how we deploy them really means doing rigorous, careful statistics. So we try out things like confidence intervals, we try out things like outlier detection, and we add more and more layers of kind of protection or kind of rigorous awareness of uncertainty or failure modes so that we can make these things more and more reliable. With that, I will wrap up, and I'd like to take any last questions you have. Yeah, thank you.
A simple question, just in terms of the learning algorithm. And it's hard to sort of explain this, but humans usually learn the same way that you described it, is that you grow up and you learn all sorts of images, you put those images inside your brain, and that way you're able to sort of identify the correct squirrel, that all fits in. If you've seen enough images and enough combinations and everything. If you're a biologist, you don't quite do that. You put together bone structure, you put together mating habits, you put together size of the tail relative to the head, all that other stuff. So the AI that you're talking about is only image-driven relative to what people do as opposed to what would be a more scientific database.
Yeah. I think that's exactly right. Yeah, so right now it's very much a question of playing this game where I hand you an input and I ask you to copy the outputs that I would have given. So like squirrel, not squirrel, fox, not fox. And the way it does that is, as you said, it's not really building up this taxonomy of big tail means this or so on, like a person might be doing. It's, it might be extracting other things. For example, in Imagenet, if it sees a lot of blue in the image, it's more likely to guess that it's a dog than a cat. And the reason is that dog pictures are more often outside than cat pictures, and blue means sky. Okay, so the algorithm might be doing these kind of funny things that are not exactly the things we would be doing. Now, we don't know what's going to happen in the next 10 years or something. You know, maybe we are going to be able to make these learning algorithms do more like what you described, which is maybe we're going to find ways of making them look at anatomically relevant information, like tail to body size and so on. But right now, they're really kind of just copying patterns that they see, that we teach them.
Normally the way people learn.
The way people learn?
Yeah. And the way I would learn growing up. I mean, I know that's a squirrel
Yeah.
because I've seen it 20,000 times. Damn it, that's a squirrel.
Yeah, actually, so I would say we actually know more about how the AIs learn than about humans learn in some sense. So it's a bit of a tough question, but yeah. Well, the reason the AI knows it's a squirrel is because it found out that like little patches of brown in exactly this part of the image mean squirrel. Yeah, yeah. We don't know that much about how people. It's a totally fascinating question. Yeah.
I thought my dad was about to ask the same question I was going to. It's going to be really weird. When you were dealing with Imagenet at the beginning and some of this nascent stuff, there's evidently a clear sort of linguistic element where, you know, a series of letters becomes text equals image,
Yeah.
and then image becomes text, and through the computer brain these two equate.
Yeah.
So was this done, because that is English, right?
Yeah.
Was that sort of done on a global scale where there was a different program that translates, or was this limited to English? Because, I mean, we're talking about English symbols here,
Yeah,
right?
yeah. Imagenet was only done in English. I think with Imagenet there's less of a barrier to translation just because the labels are all, I'd say, relatively unambiguous. Things like tiger, shark, and sewing machine, I would say, have more straightforward translations. If you look at something even more complex though, like there's something called sentiment analysis, which means I give you say a tweet and I ask you, was it happy or sad, was it angry, and so on. Now we're starting to get into a world where like translation would be very, very hard, or thinking about what this means in different contexts becomes very challenging. So yeah, Imagenet was only done in English, but it's a more simple setup. When we start in these more complex settings, yeah, they often try to do it in multiple languages because it becomes more robust, but it's hard. So yeah.
Maybe I missed something, because I'm thinking of garbage in, garbage out. And
Yeah.
What information are you gaining, are you putting in to get all these algorithms?
Mhm.
And am I
Yeah, so the information is that I've handed you pairs where someone like me or you has looked at that picture and said, that's a squirrel, okay? So we have all of this human-generated information, which is someone saying, that's a squirrel. And then we go from there, and then we learn how to copy that. We learn how to, when I give you a new picture of a squirrel, I can often know without handing it to a person that a person would say that's a squirrel. If we didn't have any such labels, it would be, who knows.
Can you come to a point where after you show so many examples, and you say, what have you learned from this? And can you ask the algorithm, can you abstract
Yeah.
out?
Yeah, that's a fascinating question. So when we say this question, how do I ask the algorithm what it's learned? Right now the algorithm, as it was built, only knows how to do one thing, which is I hand it an image and it says something out the other door, out the other side. So when I want to figure out how it's working, an engineer or a researcher needs to think of ways of either putting in images that it thinks will be helpful. Maybe you put a picture of a shark but on a weird background, and you ask, can it still tell me that's a shark? And if so, that's good. It means it's really finding the right thing, or something like that. So you have to kind of probe it and do experiments to figure out how it's working and how it learned what it learned. Yeah.
Right, so it's still more trial and error.
Yeah.
And won't abstract at this point. Like you just gave the example before where it'll come up with what dog pictures have blue in them.
Right.
So it won't abstract out and say that.
It need not do it automatically. Like there are ways you might try to kind of promote that behavior. You might encourage it to do that, but it need not do it. Remember, the rules of the game were just get the answer right as much as possible. So how might you do that? I think the current approach towards doing, as you said, which is encouraging more abstraction, is to ask it to do a lot of different things. So if I can find dogs with dog backgrounds, and then I can also find, say, dogs from videos where they're kind of off to the side, and so on. So I ask it to do a lot of different things at the same time. And if you can do a lot of different things consistently well, that's a good sign that you found robust, like, information that you might consider like more true abstraction in some sense.
On the commercialization side of it, who's interested in the work that you are doing analyzing this data?
Which one in particular are you?
Well, these data sets, I assume, are ones that you have looked at,
Mhm.
and
Yeah.
you are examining, and you're looking at their probabilities and their accuracy. Who is interested in what you are doing?
Yeah, most of these tools I would say are for, well, so I guess I should say, I work mostly at the methods layer. So I design algorithms that will do things like produce these probabilities, hopefully in a lot of different contexts. The sample I showed you, for example, with the detection, right? So this is a lot of, say, name your favorite internet company. If you have a favorite internet company, they all have this image detection problem where you hand someone an image and you want to index it for search, or you want to do whatever you want. You want to say this is a tiger shark, so when I type in tiger shark in Google, it pops up. These things are relevant in that case. A similar case is for labeling. Like I said, with medical images, it's very expensive to have a doctor go through and label. So what you want to do is you want to hand off as many of the easy cases as you can to an algorithm, but you want to let the doctor handle the hard cases like that. So these are all kind of in the air. These data sets that I showed you are all kind of scientific data sets, so you can access them on the web and use them to benchmark things. The reason we do that is so that we can collaborate with other people and index them. Tucker.
Do you think it's fair to say, in regard to the title question of your talk, can AI know what it doesn't know, that it's fair to say in a limited area, yes? Yeah?
I think that's absolutely yes.
Okay.
I think the answer is yes.
But let me ask an impertinent question. When we talk about intelligence, artificial or otherwise, we have a huge range of abilities in mind. Image identification is one of them. But I wonder, when you see movies or read books about artificial general intelligence, AGI, where it's intelligence like the full intelligence of a competent human being, does it just make you giggle at how far we have to go, and even why we would want that?
Well, why we would want that? That's a whole can of worms. Yeah, as far as like how close right now in 2021, in November 2021, how close are we to artificial general intelligence? My answer would be not that close, and I hope that some of the concrete examples I showed today, helped you take a deeper or a kind of, I'll say, more concrete look at how these algorithms would work. And I'll challenge you to think for yourself. Is that paradigm of I set up a game and I ask you to make guesses on the kind of secret points that you haven't seen before? What does that mean, right? And is that moving us towards intelligence? And the answer, we can do some impressive things, but that's what we're doing. Yeah.
I take exception. There was an article 2 days ago about, again, an AI problem that was created, artificial human that is now able to do art successfully, actually drawing successfully, and also put together a poem based on whatever data set that you've given to it that is realistically something that's good. And it was something in you may have seen that. It was something in the papers less than a week ago.
Oh, absolutely. Yeah, I mean, you can do incredible things. I guess I would just, how are you judging that it's art or not? And no, you're judging the output in some way,
Yeah.
which makes sense. It's just like, how did that output come about? And it came about through a process not dissimilar from what I
Yeah.
showed you today. Yeah, absolutely. Yeah.
Have you read or know about the book "You Look Like a Thing and I Love You" by Janelle Shane?
I'm not familiar with it.
Oh, you're not? Okay. I wanted to find out what you thought about it because it's absolutely hilarious. And that was one of the romantic lines that the AI came up with. And she was arguing, or not, well, in her book, she was arguing that AI, if people are really worried about it taking over, you know, the world, don't worry about it. We're a long way from that. But there are other parts of it. So anyways, I highly recommend the book. I laughed all the way through it.
No, I mean, it's an extremely interesting question because we can do these things like create realistic looking paintings or realistic sounding poems and so on. And it's really fantastic, and we can do things like have cars kind of more or less drive. But how is that coming about? Like, what is the process by which it's working? And it's not quite the same as you might expect.
The human expression.
Yeah.
Thank you.
All right. Before we give our speaker a final thunderous round of applause, let me urge you to save a little bit of your appreciation for Hot Monk Tavern to let Wonderfest come here. To remember that there are supporters of Wonderfest who are here kindly appearing and kindly donating. There's even a little plexiglass box back there that invites your cash donations if you're so inclined. Please don't forget that roughly 1 month from today, let's see, that's Monday, December 27th, Dr. Pascal Lee here to talk about Starship Reality Check, the science of deep space travel. All right. Thank you, Hot Monk. Thank you, Wonderfest supporters. Thank you for being here. And now, thank you, Dr. Stephen Bates.